Let me begin by saying that what an honor it is for me to have the opportunity to ask some question to Professor Tao. And to begin with, I remember a nice picture of Erdos and you. You were about 10, I think, yes. And apparently the subject was a mathematical problem. And so do you remember what was going there?
Yeah, so there was a small conference in my hometown, and my parents brought me to see him. Yeah, and he sat down with me, and he shared some problems. I wish I remembered the conversation. You know, I was 10 at the time. You know, I just thought
sure.
It was just this nice old man talking to me. So I don't remember much of anything that he said, except the one thing that struck me was that he really treated me like an adult. I think like not as he didn't speak to me like a child. But he did send me our family a postcard a couple of weeks later. You know, thank you for the nice visit. I think we invited him to our house at one point. Thank you for our visit. Let n be a natural number. Okay, the rest of the postcard was a math question, and I think that was the question that he shared with me. It's still open, actually. That question. I did look at it from time to time. I haven't actually answered that question.
Okay, and then the following year you got a bronze medal at the Mathematical Olympics, and then the subsequent year the silver one, and in 1988 the gold one. Was at that point that you decided to become a mathematician, or was just?
Well, I actually didn't. I wasn't really aware at the time that mathematician was a job. Actually, you know, at the time when people asked me what I wanted to do, I didn't know. Maybe I'll do some programming, or actually, I thought at one point maybe I'll be a shopkeeper, because you know, it seemed like the idea of I could understand how to manage inventory and you know, profits and sales. That seems like something I could do. So it was my undergraduate advisor who really persuaded me to apply for graduate school.
Professor Goldrich, yes.
Yes.
I see.
Oh yeah, he visited Italy quite a lot, actually.
Yeah. And did Erdos play any role after that?
He wrote me a letter of recommendation to get me into Princeton. I've never seen it, but I guess it worked, so okay. Yeah.
Okay. So just in 1990, when we were 15, you published, I think, your first book,
Yes.
Solving Mathematical Problems. And you said that I like mathematics because it's fun.
Yes.
And then in the second edition, you said, at that time, I enjoyed mathematics as a sport. So because you're taking a cleverly designed mathematical puzzle problem and searching for a right trick that would unlock each problem. And eventually at that time, you said that you realized that mathematics is a multifaceted subject, and our experience, you said, and appreciation changes with time and experience. And so now, 15 years later, after the second edition, is your appreciation changed, or just?
I think I still agree with my 30-year-old self. So I wrote the book when I was 15, and then I was asked to, it went out of print, actually, and then I was asked to when I was about 30, I was asked to reprint it, and I looked at the old text, and I was very embarrassed actually by some of the things I wrote, so I changed a few things, and so when I was 15, the only math I knew really was math in school and competitions, and that I enjoyed very much. And by age 30, I saw that math really was a way of thinking and a way of systematically solving problems. You know, not just mathematical problems, but real-world problems. You know, like when I have to put up a piece of furniture in my room or in my house or something, knowing how to break up a complicated problem into smaller problems. When I had to fix my computer, it's just a way of thinking, and it's something which just makes the world an easier place to live in. Like if you're not scared of as many things. There's not as many mysteries.
So Tim Gowers speak of two cultures in mathematics, saying, loosely speaking, that there are mathematicians that can be classified into theory builders and other problem solvers.
Right.
Of course, thinking of their priorities.
Mm-hmm.
Do you agree with Gower's claim? And in that case, which class do you feel to belong to?
Yeah, no, that's certainly okay. So there's a joke that there's two types of people in the world: those who like to divide people into two groups, and those who don't. So yeah, you can make these sort of distinctions. There are other people who have made similar distinctions. So like Freeman Dyson classified all scientists into birds and frogs.
Yeah, sure.
And yeah, so a frog just sort of sees just what's right in front of them, okay, and a bird sees the bigger picture. And someone else, I think...
So Dyson, I think it was...
Yeah, Freeman Dyson. And I think there's another scientist, I forgot who, used hedgehogs and foxes. Like a fox knows many things, but a hedgehog knows one thing, but knows it very, very well. And so I think all these distinctions, they're different distinctions, and they're all valid. And one thing I like about mathematics is that there are so many ways to approach it. Some of the most fun and most productive collaborations I've had is with people who think in different ways. So the distinction I like to make actually is that every collaboration needs at least one optimist and one pessimist. Someone who wants to try everything and someone who wants to be skeptical about everything. And if you have too many optimists in a project or too many pessimists, it doesn't work. But if you have one pessimist and one optimist, it works very well. And sometimes I'm the optimist, sometimes I'm the pessimist. With respect to Gower's distinction, I would say I'm much more of a problem solver than a theory builder, but some of my best collaborations actually have been with theory builders.
Yeah, I'll come back to the collaboration later on, but before, I would ask you a question. You wrote a paper titled Good Mathematics.
Oh, yes.
What's good mathematics?
Yeah, so I was asked to write this paper by the editor of this journal.
Bulletin of the American Mathematics.
Yes, the bulletin. Yeah, so Susan Freeland, she asked me to write, and so I thought about it for a long time, and I thought, is there some formula or some rule that describes what mathematics is good and what it isn't? And sort of quickly I realized that any rule you write down, you can easily think of an exception. And basically, yeah, so the point I tried to make in that article I wrote is that quality is, on the one hand, it's multidimensional. So like what I just said, like the different mathematicians have different traits and there's so many different dimensions. And it's the same with mathematics. So some mathematics is very, can be very powerful, some can be very beautiful, some can be very elegant. But maybe not all three at the same time. But the funny thing is that when mathematicians just discover a new field of mathematics or some interesting phenomenon, they all start working on it, and there's always different papers, and they're all the key papers in the subject. They're good in different ways. But if the math is good, if the math has substance to it, then it almost doesn't matter what notion of goodness you use. Like all the different notions will show up. So you will have deep results, you will have elegant results, you will have beautiful results. They'll all be present when you have a good healthy field of mathematics.
Yeah. Just in your answer, you mentioned beauty and elegance and so on. Mm-hmm. So there is any way to define this kind of concept? Very, very often the mathematicians speak of beautiful result, a beautiful theorem, a beautiful proof, or elegant proof, and so on.
Yeah.
How to explain that to ordinary people?
I think it's like art. You have to, you know it when you see it. Like it's, you see a very clever trick, and it's like, oh, okay, that was clever, or that was unexpected, or that achieved. You did a lot of mathematics with very little effort. Right? That's often a definition of elegance. Working harder without appearing to work hard. It's I don't have but outside of mathematics itself, not everything has a precise definition. We're very lucky in mathematics that we can actually precisely define things, but once you venture outside and you go into aesthetics or something, that's certainly not the case anymore.
Yeah. In the book I mentioned before, you speak of creating original argument to prove a theorem, for instance, to solve a question, and discovering more aspects of mathematics. Can mathematics be defined as a combination of creation and discovering?
Yeah, yeah. So I think the phenomena that we study, they are there. We're discovering them. But in order to understand the phenomena, like geometry or dynamics or whatever, we have to create a language that actually precisely captures real-world phenomena. So somehow, mathematics, when you start studying a field, it's creation. You're creating definitions, and it's very artificial to begin with. But as you sort of focus on what's really going on, it transitions into discovery, and you really feel like you're discovering something fundamental. That if there was some race of aliens that was also studying numbers or geometry, whatever, initially their notation might be very different from our notation, but probably the key deep theorems and results are probably very similar. So I think alien number theorists would also care very much about the Riemann hypothesis, for instance, but they would not call it the Riemann hypothesis.
So I don't remember once Kohn told me that he believed that mathematics was, say, out there. I mean, sort of Platonic reality. And so do you have this kind of...
Yeah, so as I said, it's both. There's this outer shell, which is the language that we use to see mathematics, and that's artificial, that's human. Okay, but the subject we study is I think, external, it's objective.
Mm-hmm. What makes one piece of mathematics more interesting than another one?
Well, I think it varies very much from mathematician to mathematician, and also people outside mathematics. So of course, mathematics has applications as well. And I think one of the great strengths of mathematics is that we have people with diverse approaches to mathematics and diverse interests. So some people are very geometric. Some people reason using computers, and some people reason using symbols. So my background is analysis. I very much like very vague questions of what's big and what's small, and what happens in the limit. And these are questions that are interesting to me. People with other interests in mathematics, they have different priorities, but it's great to talk with them, and sometimes you can get a fusion of insights.
Yeah. Do you prefer working in collaboration, or what you're feeling about working in isolation, or I don't know?
I like both. So it's faster to work alone, but it's more fun and satisfying to work in collaborations. And looking back, the results that I'm most proud of, they've all been joint work. They've often taken much longer to complete than if I was by myself, but much richer. And the subject is changing. 100 years ago, I think almost all papers were single author. For many reasons. I think one is that the culture was more competitive, I think, and the technology, there was no internet. You had to write letters if you wanted, or physically be in the same university to collaborate. But the culture is changing, and also mathematics is much more interdisciplinary now. It's much harder to make progress just by focusing on one tiny slice of mathematics. You have to work with many areas of mathematics, and sometimes physics and other sciences, and so you need collaboration for that. Yeah.
So for your results, you got a number of awards and acknowledgement, including, of course, field medals and other. And the question is a result of which you are particularly proud of?
I think maybe for me, because I'm not an applied mathematician, so most of my work is very theoretical. For example, the talk I gave today, this has I can guarantee zero theoretical applications of this result. Oh, indirectly maybe, but not directly. But the one work I did that actually had practical impact was my work on compressed sensing with Emmanuel Kendes and Justin Romberg, where we gave the theoretical background, the theoretical justification for a method to process images using very few measurements. And it was because we supplied the theoretical background, people realized that this technique was very, very general. So before our work, this method was used occasionally. I think seismologists, for example, used it to detect faults in the Earth's crust, and a couple other places this method had appeared. But once we had the theoretical background, like many scientists realized that this method of compressed sensing was useful in their field. And now, for example, all the most recent MRI machines, they have hard-coded in their machinery compressed sensing algorithms, and they speed up the MRI scans by a factor of up to 10 sometimes.
Yeah. In the Breakthrough Prize Mathematics Symposium, you gave a talk, and in that talk you mentioned the Polymath Project 8 on the bounded gaps between primes number. And so in the course of the development of the project, the gap has been reduced to 246. It's still far from 2. But so are you trying to prove the twin primes conjecture?
I would still love to prove the twin prime conjecture. It's not going to, we know that the methods that we worked in this Polymath project, they have a limit. I mean, maybe 246 we can get down to 242 or something, but we know, for example, we can never get beyond 6. There's a hard limit at 6. So yeah, I'm not working directly on that problem right now. There are some related problems that are harder to state that I'm still very interested in. And in fact, the work that I did with these collaborators, Matamaki, Teravainen, and Shao and Radzui, was motivated by a conjecture related to the twin prime conjecture. There's several steps, but yes, I still long-term would like to work on that conjecture, get that conjecture, but I'm not close yet.
Yeah. In that talk, you said that there is a significant niche role for Polymath's project style to play in future mathematics. And that means that Polymath's projects are a new paradigm for mathematics?
Yeah, they are an option. I think so. We're up to like 15 projects now. Of course, there are hundreds of thousands of math papers produced every year. So it's still a very, very tiny slice of all mathematics. It is very work intensive. So for these projects where hundreds and hundreds of people come online, you need one person to moderate and organize, and that's a lot of work. So I did a couple of those, and it's quite exhausting. So it's not something that scales perfectly for every situation, but there are a few. For some special projects, some projects are very well suited for breaking up into little tiny pieces and having each person work on one tiny fragment of the, and so, yeah, it's just one of many options now for how to proceed to solve a math problem.
So what about paper and pencil proofs?
Yeah, no, I was working pen and paper this morning. Yeah, that's still a very good technology. Yeah.
Okay. The first successful Polymath projects apparently were related to combinatorics and analytic number theory. And is that just a sort of limit for this kind of project, or?
It's in part because the three people, so it's myself, Tim Gowers, and Gil Kalai, who've been sort of informally running these Polymath projects. And we're all in the area of combinatorics and analysis and number theory. And we haven't had someone from other disciplines come and join us. Maybe if they did, the topic would change a bit. There are other collaborative projects in Polymath. So like, for example, there's something called the Stacks project in algebraic geometry. And this is sort of like this online textbook, like a big Wikipedia type resource for these algebraic geometry objects called stacks. So there are other projects out there in other disciplines. I'm not involved in them though. Yeah,
but you mentioned before the Polymath 15.
Yes.
That's
which one is that one?
It's upper bounding of the Bruins-Newman constant. And I think you mentioned that kind of question in the lecture you gave here in Milan 3 years ago.
Oh yes, I did. That's right. Okay.
And presenting the project, you wrote that the Riemann hypothesis is not considered as a realistic outcome of this project. So do you think that there is any chance to prove Riemann's hypothesis in the nearest future?
Not by any technique that we currently have. I think for every single method attack on the Riemann hypothesis, we pretty much know why it doesn't work. What's needed is a completely original idea, like a connection between number theory and another area of mathematics which has not yet been discovered. And maybe the connection will not first appear in connection to the Riemann hypothesis, it will appear in some other problem, and then someone will realize that it can be transferred. But I can't tell you when or if this connection is going to happen, but yeah, it's going to need something new. Yeah, pretty much, if like all the leading number theories, we always receive proofs of people who claim to prove the Riemann hypothesis, and you can open the paper and even if it's written by a professional and it's it has no obvious sort of signs of being incorrect, you can often tell there's not enough new arguments in this to possibly work. Finding the exact error may take a bit of time, but yeah, I think any proof would have to have something very striking in the first few pages that make you take notice. Like when Perelman proved the Poincare conjecture, within the first 3 or 4 pages of his paper, he had proven some very nice new inequalities about solutions to Ricci flow, which by themselves would already be an interesting paper. So you could already tell, like people were interested almost immediately when these papers came out, that there was a lot of promising new ideas. But yeah, we don't have something like that for Riemann yet.
Okay. And so Riemann hypothesis is one of the millennium problems. You are working on another of these problems, that is Navier-Stokes.
Mm-hmm. Mm-hmm.
So what?
Well, we will talk. I'll talk about that on Friday.
Okay.
Yeah. So there's. I mean, that's still a very difficult problem, whether singular solutions exist or not. If they don't, if we have global regularity, I think it's basically impossible to prove it. There's no way that any of our techniques have any chance. But if you can make singular solutions, I think there is a chance that we could answer the question in the negative, but it would take a lot of work. We'd have to build a very specific solution. Well, I will talk about this on
Okay.
Friday.
So now I just mentioned that because this, of course, is related to physics, to fluid mechanics,
Mm-hmm.
and this reminds me of a very famous paper by Wigner, which speaks of unreasonable effectiveness of
Mm-hmm.
mathematics in natural science.
Mm-hmm.
What do you think about the effectiveness of mathematics in natural sciences?
Right.
Is it just a miracle, as Wigner said, a sort of gift, or what is that?
We understand it a little better now. One explanation. So Wigner, as he said, famously argued that mathematics, it works a bit too well. I mean, the world is a messy place, and it's really surprising that there are laws of nature that we can discover and use, and we can predict the motion of the planets, and to some extent even things like economic growth or climate change or whatever. And one reason for this, there is a mathematical explanation for this actually, a partial explanation, and that's the phenomenon called universality. That if you have a system with many different, made of many different parts, like many atoms, and each atom obeys some complicated dynamics, and it's hard to solve the equations for 1 or 2 or 3 of these atoms. But if you take 1 trillion atoms together, in the limit, you often get a single law. Like the laws of thermodynamics are true for almost any system of n particles, as long as n is large enough. And it almost doesn't matter what the microscopic laws of nature are. It's like we don't actually know what the laws of nature are beyond a certain scale. Below the Planck scale, we have no unified theory of quantum mechanics and gravity. But because of universality, once you get above a certain scale, we can universal laws emerge. That's a mathematical phenomenon. I think the most famous example of universality in mathematics is the central limit theorem, that you can take any different random variables and average them together, and no matter what you start with, well, with some assumptions, you get this nice bell curve Gaussian. So I think what Wigner was observing was the phenomenon of universality at the scales that humans operate in.
Yeah. According to Attia, the result and technique arising from physics in the past century has been the lifeblood of mathematics. Could biology or neuroscience provide the lifeblood of mathematics of the future?
That's quite possible. Right now it mostly flows in the other direction, that mathematics is being used to answer questions in biology, like protein folding or identifying genes for disease and so forth. Of course, neurons have been, neural networks, machine learning was very much inspired by biological computational models. In my area of mathematics, we still, PDEs, analysis of combinatorics, still the physical sciences are by far the most influential, but now also the information sciences, so ideas from computer science have become very important. And to some extent, some of the social sciences, so sometimes I use from economics, occasionally show up actually, like game theory, for example, is a very famous example. So there are opportunities for two-way streets in every direction. Maybe eventually the humanities. That's still a way off though.
Yeah, this is related to the role of internet and computer in mathematics. What's the role of this?
So certainly on a technical level, we all use the internet.
Sure.
We all use Zoom too much. Okay, now and the way we collaborate.
I mean, big data or this kind of.
Right. Yeah. So in the future, I think better search algorithms. So one of the dreams of search engines is what's called semantic search. In mathematics, maybe I discover some nice identity, okay, and I wonder, has anyone else proven this identity before? And you can't search for it in Google because everyone has different notation, and equations don't yet have a fingerprint that you can, there's no database for equations that you can search for. Some people are working on this, but it's a very hard problem. The best way actually right now is not to use computer search, but human search. Like you can post on one of these question and answer sites, like Math Overflow. Has anyone seen this equation before? And that's the best way currently to answer these questions. So I think that will be something we'll see more of, more automated search, intelligent search, maybe automated conjecture discovery, that maybe people computers will actually find connections by extrapolating from small numerical data, and maybe they can make conjectures that then humans can try to prove. This is still very early stages for that. Yeah, and eventually maybe they can be used to find the proofs themselves, and eventually we have to change our business model. Because then if our computers can prove theorems for us, we have to do something else, like maybe direct the computers to ask what theorems that they should be looking at. I don't know, it's lots of potential.
Yeah, one of the use of computer was related to climate changes.
Mm-hmm.
So do you think that mathematics could give insight into aspect of weather and climate, or what could be the role of mathematician? And this is one of the major issue of science society today.
Right. Well, of course, all the climate models are mathematical models, and so you need the mathematicians to tell how to evaluate the models and calibrate them. They have all these parameters. And so sometimes the models, they don't give the right predictions because the parameters were not chosen correctly, or the data had some noise and we didn't account for the noise properly. There's always uncertainty. And we don't have yet, so there's still a lot of debate as to exactly which climate models are the most accurate and so forth. I think, they are, the general predictions are quite clear, like not very optimistic, to be honest, but yeah, so certainly, the mathematics has a role to play in training these climate scientists, how to make their models better, and that often, and how to test them in an objective way. We also need to do a much better job communicating what things mean. So if we say, like, for example, probability is a concept which is very unintuitive to convey to a general audience. Yeah, like if we say that there's a 30% chance that the temperature will reach this threshold or whatever, we don't do a good job of explaining to the general public what the numbers really mean.
Yeah. So you are just marginally interested in this kind of subject, or?
Well, I talk to a lot of people who work in this area. I mean, I myself work on very theoretical sides of things. But in my department, we have people who span all kinds of disciplines, and many of the applied mathematicians, they do climate modeling. So it's certainly of interest to me as a general academic.
Okay, thanks. I think I will stop here. I don't know if there are questions, or I will have to chair. That's okay. Okay, thank you very much, Professor Tan.